Hello. Uh, cool. Welcome. I'm sorry for lateness. Today it was the two-factor authentication that decided to not work on my phone, but I got it resolved. So yeah, let's go to the slides. Cool. I'm gonna share. Well, I'll paste the URL in the chat. And if that doesn't work for you, then there's always the backup, which is just the PDF or the raw Jupyter notebook, which is here. Cool. So cool. Share screen. And we're here. Whoops. All right, cool. So clicking that link, go into the slides. All right. Oh, sorry, that's the week 8 slides. I meant to post week 9. Just here. So let me, sorry. It's the last one I just posted in the chat. Because yeah, week 9 is regression, which and yeah, we'll talk about what it is and what it isn't. But I just wanted to start by saying, yeah, I think it's kind of almost not even that controversial that it's the most important topic in the class, especially like practically speaking, like just in terms of what like data scientists do on a day-to-day basis. It's really like, yeah, you're a regression doer, you know? So even all the like fancy, things that you might hear about or read about or like associate with data science, neural nets and machine learning, all that, like it literally, I'm happy to like talk about it in office hours or whatever, but there's a very like real way, like mathematically precise way in which it's all regression. It's all just like all the fancier things, neural nets and machine learning and everything. Like it's just trying to basically like once you have the structure of ordinary least squares regression in your head, every other thing is just, you can think like, oh, okay, they're trying to like solve this like issue with regression. Like they're like adding a thing onto regression. We can talk about it, but yeah, just hopefully that motivates you to yeah, understand the importance of regression. So I just wanted to start because like in class, we talked about how the regression line, right? Like the best fit, like regression is about finding in a geometric sense, it's about finding the line that best fits through a series of data points. But if you just remember that, it can be a little misleading because if you look at this figure here, like basically in the caption, you'll see like basically when if say you didn't see these lines, but you just saw the points, I think most students would, like, and in experiments they find that most students do, think that this would be the best fit line through them rather than this, right? And this actually like illustrates the reason why we have to be really careful about what we mean when we say like line of best fit, right? Because like to me, visually, I see, this set of points and I'm like, oh yeah, this is the line of best fit. It just like matches the trend of the dots, right? But in regression, when we say line of best fit, we mean a very specific thing, which is not just like it looks the best. And in fact, it's not just what this line is doing, which is minimizing the distance to all the points overall. Like meaning minimizing the distance in Euclidean space. I don't know if you know. It's like if you drew the line like from, if you drew little lines from the best fit line to all the dots here, that would be what it's minimizing, like lines going off of the line. So like this dot would be connected kind of like this. But it turns out in regression, that's not what we want, because in regression, what we want is we want the line that best predicts our y value, or like for science purposes, our dependent variable from the independent variable, which is the x, right? So the regression line of best fit is actually not the line that minimizes the distance to the dots. It's the line that minimizes the vertical distance to the dots, right? I hope that like makes sense. It's subtle, but it just is to show you that like your intuition for like the line of best fit might not match exactly what a regression is doing. And yeah, I put it in the caption here, but like the superiority of the regression line for estimating the average y given a value of x can be seen by consider the points at the extreme left of either graph, right? So even though this line overall looks like aesthetically like it fits the points, if you look over here, say if x was really low, this line is like super not good at predicting the y value from that x, right? See the line, like say the x is here, the line is way underneath like all the points for low values of x, right? See this whole cluster here of dots, like x is, or I mean, sorry, y is like sorely underpredicted for those values of x, right? Whereas here, we see that like even though it looks a little bit jankier, a little less best fit, actually like it does what we want, which is we want like a line where we can say, oh, given this value of x, I predict that the value of y will be this, right? Because here now it goes through like the average of the left-hand dots, right? Like this line, by definition, it goes through the average values of y for every given x. Cool. So, oh, it also, yeah, for like the really, really high values of x here, it also is over predicting, right? See how it's like above all these dots over here, whereas this one cuts right through the middle. So yeah, I just think this is like an amazing plot because it shows, oops, okay. Because it shows, yeah, that like you have to adjust your intuition a little bit, but once you adjust it to like not just, oh, the line that goes through the points the best, but the line that allows me to predict y from x the best, that's when you've like shifted into a regression world. Cool. So yeah, we're just estimating a line to go through points, right? And now that we know what our objective is, right? It's not just like minimizing the distance to the points, it's actually making the line that best predicts y for any given value of x. Now that we know that, yeah, we can kind of go through the slides from class and understand like the specifics, the mechanics, which is that, yes, very specifically, like a line, like you learned in pre-calc or something, math, I don't really, geometry, can be defined by like two variables, right? The slope and the intercept, which means for the intercept, we're just picking where the line starts, basically, like we're shifting the line up and down. And then for the slope, we're shifting, yeah, it's like the angle of the line, right? So with those two sort of knobs, you can imagine like there's an infinite number of lines that we could pick. And so we have to have like a criteria, right? And the criteria is, yeah, it's the line that best predicts y for all given, on average, for all given values of x. Now, like there's a terminology that I want to get straight as well, which is that like, because it'll get confusing. once there starts to be a lot of variables, for example, is like this right here, this equation, y equals a plus bx, this is like this is called like the non-fitted model, right? Because it's just variables. We haven't actually solved, right? We haven't estimated like what the best fit line is. We don't know the values of a and b that that like make that line the best fit line, right? We're just saying like, oh, there's some a and b that's gonna follow this equation, and we're estimating it, right? So I mean, like going back, right? I mean, this one also, this line here on the left also is of the form y equals a plus bx, right? But it, or yeah, a plus, is that what it was? Yeah, a plus bx. But it's not the best, it's not the regression best fit line, because this is called the principal component best fit line, right? So in this one, like we have the intercept that we can adjust, and we have the slope that we can adjust. But when we were doing principal component analysis, just like a separate thing from regression, yeah, we're trying to minimize the distance between the line and the points, like in general. Whereas here, we're just minimizing the vertical distance. Cool. So, but once we have like an objective function like that, like, oh, minimize distance to the points, or more specifically for ordinary least squares, minimize the vertical distance from the line to all the points. Once we have that, we can actually estimate the like correct value, right? In this case, we find the intercept is 23.4 and the slope is negative 1.59, right? And that's called like the fitted model. So like just if you walk into a presentation of like a data science of a data scientist, and they're like, you know, they'll have slides that are like, oh, here's my model, and then here's the fitted version, right? Like the table of results is the fitted version. Whereas like, you know, when they just have a slide saying like their general theory, like, oh, my dependent variable is this, and it's related to my independent variable this way, right? That's the not fitted yet model. Cool. And this last slide before we kind of jump into estimating regression, you should get more used to this than like these. Like these are just so to like link it to your, you know, pre-calc class and stuff that, you know, you have slope intercept form. But in data science, almost always you're gonna see it look like this, right? Just like the convention is that, yeah, your dependent variable you call y, your independent variable you call x, and then the, like, instead of saying like treating the intercept as different from the slope, actually we just consider those like a set of parameters, right? So all the parameters of the regression are just beta with a some sub number. So like beta sub 0 is the intercept, beta sub 1 is the slope on the first variable, and then this helps us because, like we'll see very soon, you're not restricted to just one independent variable, right? Later on, we can add in like any amount of independent variables that we want. It's called like multivariate regression. And then, yeah, it's easy because we can just say, oh, the first one, the slope is beta 1, but the second one, the slope is beta 2. The third one, the slope is beta 3, right? It just helps, like, because you don't know how many, like, if you're doing a project, you might have 10 variables of interest, or you might have 100. And this just lets you say, like, okay, so if I have 100, then I'll estimate beta 0 through beta 100. Whereas if I only have 10, I'll estimate beta 0 through beta 10. And then this random error term is just like kind of there to acknowledge that the line doesn't perfectly fit the dots, right? The error term is that's the vertical distance, right? We're trying to find the values of beta 0 and beta 1 that minimize the vertical distance between our line and the points, the data points. But yeah, this right here is like what's left over, right? Meaning that the line's not going to be able to fit the points perfectly. There's going to be this error, and so those error values are epsilon. Sorry, I should have said that's the Greek letter epsilon. So yeah, with all this together, like, oh, and sorry, I should have said there's these like letters I, and that just means like each data point, right? So like when I is 0, you could think of it like that's the very first data point. I1 is when I equals 1, that's the second data point. When I equals 2, that's the third data point, right? So each data point has an x value, an x coordinate, a y coordinate, and then, yeah, the error that's left over when we fit our line between the line and that point, vertical distance. Cool. So how do we do it in Python? Well, that's stats models. And I don't know about you, but I really hate how like stats models has two different ways of importing it. Like one is just statsmodels.api as SM, but then for actually like doing a regression, fitting a regression, it's statsmodels.formula.api as SMF. So like if you look at the slides or you look at like Prof. JR's example code, you'll see, yeah, there's two import statements, but for the purposes of like this, just the purposes of like just purely, oh, I want to run a regression really quickly. I'm not worried about like diagnostic plots or, yeah, going into the weeds, the details of it. This is the one you want to import, is statsmodels.formula.api. And the only difference is like statsmodels.api uses sort of this like Python, like they tried to make the functions and everything look very like Pythonic is the word for it, like make it natural to Python coders, but statsmodels.formula.api, right? Meaning the version with formula in it is made to be more natural for like social scientists or just scientists in general, because it lets you, instead of like writing everything as a Python function, you'll see like it lets us write equations like more like this one. Like we can almost write something that's almost exactly like this, but with a tilde instead of an equal sign is basically the only difference. And statsmodels.formula.api will like convert it into code basically. So that's why we use statsmodels.formula. I'll come back to that in a minute, but yeah, we're gonna do a regression on this data set, which is just like, I just got a data set on years since independence of every country in the world, and then a data set on the average life expectancy of people in that country. Because like for my dissertation, I study like the effects of history on the present, long story short. And so it's stuff like this, right? Like what was the effect of colonization on like public health in these places? Like did the colonial powers develop like robust public health infrastructure comparable to their own, right? Like did Barbados have the same provision of public health as like England or not, right? I mean, you probably have a preconceived notion if you've like learned history or you're from like a former colony, but yeah, the point is like we can use regression to like analytically like get a number for, in this case, we're going to look at like what was the effect of an additional year of colonization basically on life expectancy. And just give me a minute because the cat is eating something as always. Okay, sorry about that. So yeah, we're looking at this data set, and as Prof. JR and Sperling always do at the beginning, right? Like you should load it. We use our standard like pandas and numpy imports. And then we use pd.read.csv. I just called it colonial life expectancy.csv, and it's in the same like folder as the Python notebook. So I don't have to worry about file paths or anything. I just give it the name of the file as a string, and it loads it. And then I just like display it. I could have done .head, but actually sometimes it depends on like what I'm doing, and it depends on how messy the data is. But yeah, sometimes I do .head, and that will just show me like, oh, what columns there are. But here it's like, I also just want to see like the range of values. And so not putting .head helps because it also shows you the last 5, right? So I see like, okay, they're in alphabetical order from Afghanistan to Zimbabwe, and it just has like the independence date, which is not that helpful for us, but years since independence is helpful. That's going to be our independent variable. And then it has the year that the life expectancy was recorded, and then it has the average life expectancy for that country, right? Which is going to be our dependent variable. So it's like really simple. Usually we'll have often you'll have a much messier data set, and you'll have to like, I mean, it was messy when I first got it. Like I had to compute the years since independence and stuff, but I did that on the side. But yeah, the point is usually like you'll have to do some work before you can get it into the form where it's just like, bam, all right, I have a number in this column, and I have a number in this column, and I want to do my regression that way. But yeah, we're looking at regression, not data cleaning right now, so that's why. Yeah, exploratory data analysis. That's like the name for not just running the regression right when you start, because even like, it's weird, it's funny, right? Because even this data I kind of chose after like considering a bunch of data sets, but the other data sets were like even more like messy and weird. But even this data set has some like quirks and some weirdness and some yeah, just some like idiosyncrasies. So exploratory data analysis is something that you actually need to do, even though it will be very tempting to just be like, all right, I'm going to load my data set, and I'm just going to click the regression button, and I'm just going to run it, right? Exploratory data analysis is just stuff like making graphs or looking at the like descriptive statistics of the variables, like, you know, mean and median and the outliers and everything. So yeah, I mean, at a basic level, even though like stuff can go wrong, very wrong, even with doing this, like at a basic level, you want to plot some like scatter plots, or this is a box and whiskers plot of your variables, just so you can see like, okay, what am I working with, right? So I like this one for this variable because like it just shows me, all right, here are the ends of the variable values, right? Like the lowest one is around 50 and the highest one's around 85. Yeah, I think this one's, well, we'll see, right? Because the point is like, we see this and we might start thinking like, okay, what's the low one and what's the high one? Like, and is there like a skew? Like it looks like it's also skewed left, right? Meaning like the mean is right here. It's this little yellow orange line. And like the values spread much more out to the left, and they're more like packed in on the right, right? So this is a bit skewed. I can't remember if that's technically, I guess that's called skewed left, but feel free to correct. I always just have to Google like the skew. Does that mean like, but you get it. It's not like a bell curve. It's like, it's a bell curve, but with a lot more like width on the left, to the left of the mean than to the right of it. So, oh yeah, and I just put this because like people had gotten confused about some of the code I'm writing, and like when you see these, I usually just like put these URLs in comments in my code to just show like, oh, I didn't memorize like how plt.tick params work. I just like went here because I wanted the box and whisker plot, or the box plot, produces all these weird like labels and stuff all over the place that I didn't want. And so yeah, just like this is annotating like this, that you haven't seen this like tick params thing before. I hadn't really seen it before, but I Googled like how to remove y-axis labels in Matplotlib. That's all. Oh, but one thing that I think is important is like vert. There's this argument to boxplot, which is vert, right? And it's for vertical. So by default, it's like this plot is like up and down. But I don't know about any of you, but to me, like reading left to right makes sense. I mean, just because most languages, are there languages that do, I guess like some people, when I was in like China and stuff, read top to bottom, but I think like, yeah, if you're used to reading things left to right, like sort of almost psychologically, it seems like you should put vert equals false. It just helps me to read things left to right from like lowest value to highest value rather than bottom to top for these types of plots. I don't know, maybe that's just because like in high school and stuff, this is how I learned to do it, is like horizontally. So that's what that is. And yeah, like, you know, you look at this and you should be thinking like, what are the outliers, right? It would help me to know, like, because sometimes an outlier can be something very weird. Like sometimes in these country data sets, they'll include places like Vatican City or like, trying to think of another example, Vatican's, or there's this thing called the Order of Malta, which is like the most bizarre quote unquote country because it doesn't actually have any land. Like the Order of Malta is like a group of people, but they have like an embassy in like Italy and stuff. You can look it up. Like it's not the country Malta. The country called Malta is different from the Order of Malta. Very weird. Malta is like a country with land and stuff, but the Order of Malta is like a country, like theoretically. Yeah, anyway, the point is like sometimes they include like entities like that, which can like really throw off the data set, right? Because like, for example, like Vatican City, it's just like the Pope and like priests, right? And so it's kind of a weird thing if you're like worried about, you know, colonialism, right? It's kind of like that's not really the type of population unit we're interested in, right? So just all this like, and that's like a weird example. There's more obvious examples in other data sets, but the point is just like, you really, I think, want to look at the outliers because you might see like, oh wait, actually I shouldn't include those in this analysis, right? You might find that. But in this case, yeah, we see like, no, the outliers actually are just like straightforward, like sovereign countries that like are self-governing, right? Like if they included like Western Sahara or like Palestine or places like that, it also could get tricky because it's like, you know, those places they don't like govern themselves. You know what I mean? Okay, controversy about Palestine, but Western Sahara definitely doesn't govern itself, let's say, right? So, but we see like, okay, it's like Lesotho, right? Yeah, that's pronounced Lesotho, it turns out. I had like a friend who was like from there, which is like very weird. Like I've met one person ever from there and like they're like one of my close friends. But yeah, it's Lesotho. Like it's hard, it's like tu. It's like Arabic and Hindi have like a du. Anyway, Lesotho. And it's yeah, that has the lowest life expectancy in the world. Central African Republic, Sierra Leone, Chad, and Cote d'Ivoire. Yeah, you maybe see a pattern for these. And you may also see a pattern for these, right? The highest life expectancy ones. So already we have like, these are all like besides Chad, which is like mid-Saharan, these are all sub-Saharan African countries, right, that were colonized. And in these highest ones, we have Singapore, Australia, Spain, Switzerland, Japan. Japan, notorious colonizer. Spain, notorious colonizer. Switzerland, interesting, because they didn't have colonies, I think. Like, yeah, I think they didn't. Yeah, they didn't, because like, I don't even, yeah. Anyway, it's like Austro-Hungarian Habsburg stuff. But yeah, the point is like, we're just looking at it and we're just kind of already seeing things pertaining to our hypothesis, right? Which is like, oh, I should have made it explicit, like in a regression, right? the hypothesis, I talked about it last week, the hypothesis is always like, the null hypothesis is, oh, my independent variable has no effect on my dependent variable, right? Whereas the alternative hypothesis is, oh, actually, no, there is like an effect happening here. The independent variable, it does have an effect on the dependent variable, right? So in this case, like we already see, like, even though we just did it because we were interested in these outliers, like not only does it help us breathe easier, like, oh, we don't need to remove anything. These are all the countries that I was thinking of. You know, these are all the, yeah, these are all the types of units that I want to study, but also like, we're like, oh, wow, even just looking at the outliers, we have the beginnings of evidence that like, oh, there's probably an effect of colonialism on life expectancy, right? I mean, Singapore is a former colony, right? It's like Malaya. Yeah, so that one's a former colony that has like absurdly high life expectancy, right? And then Australia is like a settler colony, but the rest are, yeah, European or Japanese, yeah, Euro-Japanese, the colonial powers basically. And if I extended it to have like top 10, you'd see like, you know, like Germany and France and all those places. So yeah, the next thing we can do right now, so the box plot is like, oh, I'm interested in exploratory data analysis of a single variable. The scatter plot is kind of the most basic thing to look at relationship between two variables, right? And what we see is like, well, okay, now that we look at this, it gets a little weird in the sense that we still probably think like our hypothesis makes sense, that more years since independence lead to a higher life expectancy, right? But looking at this, it's kind of like, I don't really think it's linear, right? It's probably more like a, yeah, like some sort of logarithmic. Well, the point is it's a curve that like, as you look, like if you get independence at all to like having 50 years of it, you build up like your public health infrastructure in a huge way, right? And I mean, that's what we see like in post World War II history, right? Is like countries get independence and the really like, let's say like functional ones, like put a ton of money and time and everything into developing public health infrastructure, right? Like vaccinations and what's it, like child health, like what's it called, like oh, what's the name for it? Yeah, just like healthy birth practices and all that. So, but it's so like actually like there's this, it's probably like at the very beginning, yeah, it shoots up, and then over time, like there's diminishing returns is the name for this, which is like, yeah, once you get your public health infrastructure to a certain level, it's like hard to, you can't like keep investing money or resources into public health and get the life expectancy to like 200, right? It just kind of like levels out at like 80-ish. So all that is just a caveat that like when we, this whole linear regression thing, like it's restricted to just a line, right? Which is probably not the best way to model this. It's probably not a line, it's a curve that goes like this. And that goes all the way back to like my first slide, which is like all the learning and all that like fancy stuff. One of the main things that it's correcting, or yeah, kind of correcting for, is like, how can we do regression type things where we like see the quantitative impact of one variable on the other, but have it not be restricted to a line, right? Like a neural net is like just called like a universal function approximator, which means like it can actually fit, you know, it can like find value, like you can think of it like it can find values of the relationship between variables that are any, like that look like anything. Like it could look like a sine wave, it could look like a curve that goes like this, it could look like a curve that goes like this, it could you know, do a bunch of stuff. And the neural net will be able to find that pattern, like mathematically, like it's capable of finding nonlinear patterns. So that's why neural nets are so powerful. If you have read about them in like the news, how they just beat every other method. Yeah, they're just universal nonlinear function approximators. Whereas a regression, linear regression is just a like universal linear function approximator, right? It can only find functions that are like, oh, I can move it up and down, and I can change the slope, right? I can change the angle, but that's it. I can't model these like turns, these curves. But just so you know, like we're restricted to linear regression, not because like we think it's the best, but because we have to learn how to do linear regression because the nonlinear regressions, they're just all like we start with the linear regression model, and then we remove the restriction that it has to be aligned, just so you know. Another thing is like, so we see that a ton, right? Like most of the points are clustered down here near like 0, right? And again, that makes sense because like most countries in the world are countries that got their independence post World War II, right? I think I read like it's like at when World War II ended, there were like 40 countries in the world, right? And now there's 180. Well, in this data set, there's 183. So yeah, it's like a huge explosion because of decolonization. So it makes sense. But another thing, it's like you're not responsible for it right now in the class, but like it's just so important and ubiquitous that I wanted to mention it, which is like when you have a skew variable like that, where a ton of the values are clustered down here, and then there's a few that are like super extreme, like 1,000. What you really want to do usually is like take the logarithm, and you don't have to worry about like the math of why that is. Like I spent a lot of time when I was in like high school worrying about like, wait, why does the log de-skew it, right? And I guess I eventually kind of got it, but for your sake, for your purposes, like I still don't get it. And for your purposes, just think of it as like a log is like a de-skewing operation, right? Meaning it just takes skewed distributions and like flattens them, or like spreads them out more evenly. That's the best way I can think to describe it. It's just a transformation on the variable that makes it more, right? Like look at how clustered, again, looking left to right, look at how clustered the points are down here with a non-logged version. And then look here where it's like, there's just a property of the logarithm that it takes things that look skewed to us as humans and it makes them look less skewed. And what's cool also is that like regressions work just as well with non-logarithm versions of the variables and logarithm versions, in the sense that like for the rest of this, we're gonna just keep it not logged. This is just to show you, like, this is like a sidebar, but when we read the regression results like in class and it's like, oh, an increase in the independent variable of 1 unit leads to an increase or decrease of the dependent variable of this many units. When you are working with log variables, you just have to change that interpretation a little bit, where if you've logged a variable, it just becomes a 1% change in the variable, right? So not a 1 unit change, but a 1% change. So in this case, like, right, in the non-log version, we could say like 1 additional year of independence has the effect of this much higher life expectancy. Whereas here, since we've logged years since independence, we would say something like, 1% longer time since independence has this effect on life expectancy, right? It's a little weird for this one. It makes a lot more sense if you do like, weight or something. Like if it was like weight and then like heart health, you could be like, oh, if you decrease your weight by like, by 1% of what it is right now, it'll have this effect, right? So that's logs. Logs are just like percent scale, right? That's all it does. It converts the variable from the unit of the variable itself to like percent changes in the variable. So anyway, yeah, I talked about this already, that putting it in the language of our model, it's just, the null hypothesis is always the conservative one, like, oh, I don't think I'm right, I'm trying to prove things wrong, right? I'm trying to falsify things. So I think there's just no effect of the independent variable on the dependent variable. Whereas our alternative hypothesis is like, oh, actually, we can't reject, right? We fail to reject the null. Like we fail to reject that there's an effect of the independent variable on the dependent. Cool. And this is the key slide, right? Because it shows that just in technically, yeah, 2 lines of code. I had to put this so that it would fit on the slide. So like, please don't worry about this line right here. It's this line and this line that are the key here, because this line right here is what I was talking about, where like the stats models.formula.api rather than just stats models.api. That lets us create these strings. These are just called like formula strings. And all it is like you put your dependent variable on the left, right? Just like in the equation that we saw earlier. And then you put all of your independent variables. In this case, we just have one independent variable. But if we had more, we would just put them all on the right side of the tilde, right? This tilde character, it's like on your keyboard. If it's like a US keyboard, it's like shift. You hold down shift and then it's the key next to the left of 1. But yeah, so all we do is we make this string, right? Dependent variable, tilde, independent variable. And like where that comes from is we look at the actual names of the columns in the data set, right? So in this case, YRS_since_int is our independent variable, and life_x is our dependent. So that's what we put in this formula string, right? And then the most important argument though is you have to tell it like what your data frame is. So in this case, we say, oh, the data is from colonial DF. That's what I called the data frame that I loaded earlier. Now, you might look at this and say like, okay, cool. So this is doing the regression, right? But this is why I made such a big deal out of like fit versus non-fit, fitted model versus non-fitted model, which is just like, because this right here, this just tells stats models what your model is, right? And then why do we have to add .fit at the end? That's because like once we tell it the model, there's a second step, like just always in any of these procedures, which is like actually turns out to be really important, especially when you do the fancier machine learning stuff, which is like, okay, now that you know what the model is, right? Now that we've defined our model, its life expectancy, has some relation to years since independence. Then we have to do .fit. .fit is what says like, okay, stats models go, like find the line, right? Like try out it literally, you can imagine like it tries out a bunch of different lines, and you can imagine like it just puts down a random line, and then it finds like how bad it does at predicting the y from x, and then it like shifts the line a little bit, shifts the line, and eventually it gets a line where it's like, oh, I can't move this line anymore to make the distances, right, make the prediction of y given x any better. So that's .fit. That's like telling it to start running a procedure of estimation, right? And when that line finishes, results, it holds it's like a big like Python object that has a bunch of stuff in it. And what we want is this .summary, right? So we do, usually just in your cell, you can just type results.summary and run it. Like I said, I had to do this extra stuff because I had to like compactify it to fit on the slide. But yeah, and the point is like you get this table, and it's kind of annoying because all this stuff here, it's like you're almost never going to look at. Maybe r squared, but you're almost never going to look at it. Maybe number of observations. This stuff here, you're definitely almost never going to look at, like just never. So it's just annoying because like they give you all this stuff, and actually it's this little table right here in the middle, like just for some reason stuck right in the middle. That's like, that's what you want to look at. That's the results of the regression. My favorite like stats textbook, it's called Rethinking Statistics. It just like has a version of like results.summary that just throws everything out besides this table. So like, just so you know, this is what matters. And I know we're running close on time, so I'll just summarize this, which is like, it's just telling you that coef is, those are the betas that we talked about earlier, right? So here beta 0 is 69.587. So you can imagine that as like, that's the starting point for life expectancy, meaning like on average, if a country had 0 years since independence, if a country just suddenly becomes independent right now, right? Like South Sudan, I think, is like the most recent like independent country in the world, 2013, I think. Yeah, yeah. Then, so with 0 years of independence, we expect our dependent variable, the life expectancy, to be about 69.5 years, right? And then we have the slope, right? So that's the intercept. So it's intercept, so that's easy. Then we have to remember that this is the slope on years since independence. What that means is, yeah, for every additional year of independence, on average, the life expectancy goes up by like 0.0, rounded, that's about 0.02 years, right? Which is like, it seems like a small effect, but like, think about, that's 1 year, right? So after like a decade, that's like 0.1 years, right? And after like a century, that's like more than a year, right? So the point is like, you're starting to get more years of people's lives as you get like decade or dozens and like then especially hundreds of years of independence, right? Which makes sense given our knowledge of like history. But the point of regression is not to like discover something totally new. It's to sort of get a quantitative like estimation of precise effects, right? And so the only other thing that is worth noting is like, it's frustrating because it's a T score rather than a Z score, but like as our secret, you can just think of these as like Z scores. And if you remember what the Z scores look like you can take a Z score and you can like plot it on the bell curve on the normal distribution, and it shows you like how extreme that value is. So like this right here, 109.483, that's like, so it's 109 standard deviations above what we would expect from random chance, right? And in this case, T is 5.96, so it's almost like 6 standard deviations above what we'd expect by chance. And what that means is our p-value, right, that's what this column is just like 0. Like it's so low. It's like 0.00000000001 maybe, right? Because it's just so unlikely that these values happened by chance, which, yeah, leads us to reject our null hypothesis, right? Like these effects, the effect of years since independence on life expectancy is like so strong and sort of, yeah, like out of the ordinary, let's say, like out of what you'd expect if life expectancy was just kind of random between countries, right? Like if years since independence had made no difference and life expectancy was just all over the place, it didn't matter how long you were independent for. It's like not that. The pattern is so strong that, yeah, we reject the null hypothesis at like every confidence level. And this is just extra, but yeah, Seaborn, which we talked about in class, has this thing called reg plot, right? So regression plot, and I kind of love it. And it's actually like what I do in general, because it just instantly like gives you the scatter plot, right? But also the regression line. And then also this confidence interval, which we haven't talked about, but this little like light blue band shows you how confident it is, right? So out here, there are fewer data points, like way out here near 1,000. So it's like less confident. It's like, oh, I don't know. It could be up here, but it could be down here. Whereas down here, we have a ton of points. So it's like really confident, right? And the point is we just see this upward slope. And that's, you know, that's like a visual representation of, yeah, of our effect. And the way, this is kind of hard to like describe, but visually, the way that we know that our null hypothesis is rejected here is that you couldn't fit a flat line on inside this confidence band, right? Like see this confidence band? There's no way I could fit a flat line through it. But if your null hypothesis isn't rejected, like if it's not that strong, you'll see the confidence band gets really big because it's like, oh, I don't actually know. I don't think it like, it could be sloped up, but it could be just sloped flat, right? No effect. And so you'll see that, right? Like if you did this reg plot with your own data set, you might see the band is like really big. And if you can fit like a flat line through the band, that kind of means like, oh, we can't reject that there might be no effect, right? Hopefully that makes sense. Like in this case, even it's not the line you want to look at, because the line is just one like particular estimate. It's the band you want to look at, because the band says like these are like the plausible values of the regression line given different, like if the data was a little bit different, is how you want to think about that, right? And so again, all that is just to say, like, you're going to be tempted to like look at the line and be like, oh, it slopes up, therefore like positive effect, and I reject the null. But it's not actually like whether the line slopes up, it's actually whether you could fit a flat line into the confidence band. So there's a bunch of other stuff, but I call them appendix, right? Because you can just look at them at your own time. Talking about removing outliers if we wanted to, and then there's another one about going into more detail about taking logarithms. So yeah, that's all. Thanks. And homework 3, I will talk about it next section, or whatever the section is after it's due. So I guess that's next section. Yeah, I'll go over it, like I'll try to go over it more than like I went over homework 2, for example, because yeah, I got feedback that like that's what y'all are worried about, and I totally get that. I can't talk about it until like it's due. I can talk about it in office hours, but it has to be like private, because they're like, oh, we don't want students like, I don't know why this, but anyway, we can talk about the homework in private office hours or over email. I tried to respond to some emails. I know I didn't get to all of them, but then I will talk about it to everyone next week. Yeah.